the way we start this procedure is we initialize k Gaussians randomly. Right? So randomly is good, but k is bad. How do you know how many Gaussians you need for your data set? And the answer ends up being as difficult, almost as difficult as it is for k-means. It's a little bit different in this case, because in this case you have k-means, it's a rather ad hoc algorithm. When you're doing mixture models, you are in the probabilistic space, so you know what you're doing. You're trying to minimize a certain quantity, and specifically what you're doing is you're maximizing the likelihood of the data under the mixture model that you've created. So your mixture model has k components, and each one of those components assigns a probability to each of the points xi, right? Each component in real value data, it's just a Gaussian. Right, so this quantity p of xi given k, that's just modeled by a Gaussian. So what you're doing is, for each data point, you're seeing how probable is that data point under each of the Gaussians multiplied by the priors. How many points the Gaussian is supposed to be responsible for. And what EM is trying to do implicitly is, it's called it's the expectation maximization algorithm. It tries to maximize the likelihood of your data. Or another way to say it, it tries to fit the Gaussians to the data. So what you might want to do is you might want to say, okay, so I'm trying to fit the data as best as I can, so maybe I should pick k based on whatever mixture model gives me the best fit to the data. And unfortunately, that is an ill-posed way of selecting k, because the likelihood is going to get higher and higher as you add more and more components to the mixture. It's the same thing that happens with k-means. Right? Remember, in k-means, the lowest variance within clusters that you could get is if you place a centroid on each data point. Then the variance is 0 in all the clusters. The same thing happens here. Imagine that you place a little Gaussian over every point in your space, right? And make the variance of that Gaussian really, really small. So what's going to happen then is you're going to have a bunch of spikes just over the data points. The likelihood of the data is going to be very high because each Gaussian is going to assign all of its probability mass to just one data point. So the likelihood is going to be very, very high. It's going to look like you have a very good fit to the data, but it's not a useful fit. Because if you get new data points that you haven't seen before, the probability assigned to those data points is going to be 0. So it's not a very good mixture model for that. So you don't want to do that. Now you could play the same trick that you did with k-means. So you could introduce a training set and a validation set and fit a Gaussian based on the training set. So find the means and the variances based on the training set, and then see which number of components does the best on the validation set. That sometimes works, but in many domains you still get best performance when you have as many components as you have instances in the training set. So another way to think about it, sort of the more Gaussians you throw, the more densely you're going to cover the space. So there is, because the model is probabilistic, however, there are other ways in which you could select the number of components, k. So, and the idea is, it's this really old idea in mathematics. It's when you have certain observations, often you can explain the observations in a number of different ways. And in that case, what you should do, what you should prefer is you should prefer the simplest possible observation. So if you have a certain phenomenon, certain numbers coming out, if you can explain them in this way and in that way and in that way, you should always pick the simplest. It's a pretty good it's a pretty good strategy. It's called Occam's razor. There are two possible instantiations of Occam's razor for mixture models. So they're known as Bayes information criterion and a Akaike information criterion. And what you're trying to do in both cases is you're trying to balance the likelihood against the complexity of the model. Now, the likelihood, remember, the more complicated the model, the more components you throw at it, the higher the likelihood is going to be. So you want to take that likelihood, it's L in the Bayes information criterion, and offset it by the complexity of the model. And in Akaike, you do pretty much the same thing, only you minimize. So you take the complexity and subtract from it the likelihood. This quantity, 1/2 p log n, and this quantity, 2p, those are reflections of how complicated the model is. And what they're based on is they're based on this parameter p. And p is the number of, it's sort of the number of parameters that you have in the model. What it's talking about in the general sense of the word, you're talking about the total number of parameters, not the number of Gaussians, but the total number of parameters involved. So if I was doing it in one dimension, each Gaussian has how many parameters? 2, right? So if I have a mixture of 2 Gaussians, how many parameters does it have? 4, no, 5. It is 5, because you need a prior, right? Don't forget the priors. They're also parameters. But if I had 10-dimensional space, then each one of my Gaussians would have 10 numbers for the mean. It would also have about 50 numbers for the covariance matrix, right? And then you would have 9, and then however many Gaussians you have, you multiply those numbers by that. And if k is the number of Gaussians, then you also have k minus 1 parameters for the priors. So that would be your p. And p basically reflects how complicated, how rich your model is. So these are 2 different ways of combining likelihood with the complexity of the model. I'm not going to spend much time talking about them. These methods, they have some nice theoretical underpinning, and they are attractive sort of from a conceptual point of view, because you're explicitly doing Occam's razor. In practice, this is not something you want to do. In practice, you usually the reason you do mixture models, the reason you run the EM algorithm, is you're trying to re-represent your data for some follow-on task. So, for example, you're taking your high-dimensional data, you're modeling it with 100 Gaussians, and then you're going to use which points were assigned to which Gaussian as a new representation of the data. And then you're going to feed that representation maybe to a classifier. So a better way to pick the number of components is to see which number of components results in the best performance for your classifier, not which one of them maximizes one of these criteria, because these are somewhat arbitrary.